Okay, welcome back. After last lecture, I'm glad to have you back because it was quite involved and frankly, it's a naming convention thing. It's not the chemistry that tends to bother beginning students in organic chemistry. It's the naming. Just like in general chemistry, oftentimes it's the math rather than the chemistry that gets you here. It's the complex naming conventions that tend to bother anyone more than any of the real chemistry. So glad to have you back. Hopefully, if you haven't mastered the naming, you're still working on it. But let's take a little break from that and talk about something that really doesn't rely on your understanding of IUPAC naming conventions too much. Okay, so as you see, we're going to talk here about properties of alkanes. Because they're relatively simple, they're mostly carbon and hydrogen, they don't tend to do a lot of chemistry, so that's actually good. It keeps the properties of alkanes pretty simple and gives us something that's pretty easy to follow after that naming lecture that could be, unfortunately, at times quite convoluted. All right, so let's start by talking about the physical states of the alkanes. So alkanes are gases when they only have a 1 to 4 carbon atoms. This is at room temperature and pressure, of course, because propane and butane are pretty easily liquefied. They're liquids at room temperature and pressure when they have 5 to 8 carbon atoms, and that's why our octane is our principal component of gasoline, because it's the largest carbon count that's still a liquid. Because it's convenient to pump it as a liquid, right? Solids start typically when you have 9 to 17 carbon atoms for the alkanes, or even larger, but we tend not to worry about things much larger than that for this course, at least in this section. So it's much easier to pump a liquid than a solid, but in order to get as much energy stored in those bonds as possible, we tend to want that 8 carbon atom liquid, because that's a very, very energy dense molecule. Okay, so these are our rules of thumb. Gases between 1 and 4 carbon atoms long for the alkane, at least the straight chain alkanes, liquids from 5 to 8 carbon atoms long, and then solids from 9 to whatever, but we tend to stop carrying at this section after about 17 carbon atoms. Okay, so that image may look familiar from our very first lecture on chapter 11. We saw the oil and water image, but now we're talking specifically about alkanes. So alkanes, without exception, are nonpolar. Therefore, they're insoluble in water. They're less dense than water, with a density that ranges from about 0.62 grams per milliliter to about 0.79 grams per milliliter for the common alkanes that we encounter. So here, vegetable oil, an organic compound, is not soluble in water. Vegetable oil is not just an alkane, but it does behave like an alkane, so that's why we show that image there. So alkanes are pretty typical in how they behave, and they don't do a whole lot, so they're actually pretty easy for beginning students. You've got enough to deal with naming them. Now at least we've got some pretty safe common behaviors that don't have a whole lot of exceptions and aren't very complex when we get into properties here. All right, as a result of that nonpolar behavior of alkanes, when we deal with alkanes in an oil spill, the alkanes in the oil do not mix with the water. The alkanes will form a thin layer on the surface because of their low density and their nonpolar nature, and they can spread out very far distances. That's one of the big problems with having an oil spill, and we've had, unfortunately, a number of major oil spills over the last several decades. Cleanup typically involves mechanical, chemical, and microbiological methods. So those are ways to either just mechanically try to clean up the spill by agitating that water. Chemically, we can try to use things that will adsorb the alkanes so that we can soak them up into some inert material and get them out of the ecosystem. And finally, microbiologically, there are certain microbes that can break down these alkanes into simpler alkanes. And as we said, alkanes 1 to 4 are gases. So if we can make some methane or ethane gas, it's not great. It puts it out into the environment, but at least it gets it off the surface of the water. We see here in our picture that that's a big challenge because they spread out huge distances. You can, affect wildlife, certainly birds and aquatic life are damaged by the results of the oil spills. So we do what we can to try to clean it up, but hopefully the best thing is not to have it happen in the first place. Okay, if we look at melting and boiling points for the alkanes, they're pretty typical of organic compounds, although they do tend to be the lowest melting and boiling of all the organic compounds because of their nonpolar nature and their limited um, interactions between molecules. They have the London or dispersion forces you learned about back in Chem 141, and that's about all. Otherwise, they really don't, being nonpolar substances, they really don't have any other types of interactions. Those weak dispersion or London forces, as you may have learned them, do get more significant when you have more carbons in the chain. So that's why you go from being gases at things like methane, ethane, propane, and butane to being liquids starting at pentane at room temperature and pressure, and then finally solids once we hit nonane. That's a consequence of these weak dispersion forces. We say weak, but when you've got 9 carbons in the chain, individually they're weak, but when you have that many, you can start to get significant interactions, and that's why you see that difference, the increase in boiling point and um, uh, number of carbon atoms for the alkanes. So far, we've been talking about the straight chain alkanes, but as you learned in the last lecture, those branches really matter. And so if we're comparing branched alkanes with the straight chain alkanes, again, if we're looking at, say, structural isomers, where they have the same overall number of carbon and hydrogen atoms, what we see with the branched alkanes is that they have lower melting and boiling points than the straight chain alkanes. And we see that in the pictures, both the skeletal structures where you can see those hexane molecules being able to line up really nicely, the skeletal structures one on top of the other to make those zigzags, compared with the 2,3-dimethylbutane molecules not being able to get as compact. And then we have the licorice stick and tennis ball analogy as well. You just don't have as many surfaces for contact. You can't have the London or dispersion forces as significant when you have a branched alkane as you can when you have a straight chain alkane. So hexane has a boiling point of 69 degrees Celsius at standard pressure, whereas 3-methylpentane has a boiling point of 63 degrees Celsius, and 2,3-dimethylbutane has a boiling point of 58. So the more highly branched we get, the less significant the dispersion force is, and therefore the lower the boiling point. So that's hopefully makes sense to you, if not with the structural formulas, at least with the licorice and tennis ball analogies. We also talked about cycloalkanes, so let's talk about their properties. Their melting and boiling points are actually higher than the straight chain alkanes, and certainly then higher than the branched chain alkanes, as we saw before. And that has to do with that restricted rotation. Because you're in a rigid ring, you can't have free rotation around every carbon-carbon bond, which means you can really pack in tightly and maximize those London or dispersion forces. So if we're looking at structural isomers here, regular old pentane has a boiling point of 36. Then the branched chain varieties, as we see there, 2-methylbutane, 28 degrees Celsius for its boiling point, dimethylpropane, 10 degrees Celsius. But when we look at cyclopentane, which actually is 2 hydrogens less than regular old pentane, has a boiling point significantly higher at 49 degrees Celsius, because those cycloalkanes, the molecules can line up perfectly with each other to maximize their London or dispersion forces. So for the same reason that the branched alkanes have lower boiling points because they can't pack in as well, the cycloalkanes have higher boiling points than their corresponding straight chain analogs because they can pack in very highly. All right, let's see how you do on the properties, specifically the melting and boiling point properties of the alkanes with this learning check. For the following pair of hydrocarbons, which one has the higher boiling point and why? So number 1, butane or octane. Pick which one you'd expect to have the higher boiling point and explain why. And then number 2, hexane or 2,3-dimethylbutane. Select which of those two would be expected to have the higher boiling point and then give a reason why. So please pause the video here while you do that work and start it back up, and we'll check and see if we got the same answers. All right, so for number 1, we're dealing with straight chain alkanes, and butane compared with octane? Well, butane's a 4-carbon chain, octane's an 8-carbon chain. So octane, we'd expect to have the higher boiling point because the rule is the more carbon atoms in a straight chain alkane, the higher the boiling point. For number 2, oh, it also, of course, if you wanted to get really technical, it has to do with the magnitude of the London or dispersion forces. The more carbon atoms you have, the more places you have for those London or dispersion forces to interact with one another. For number 2, hexane or 2,3-dimethylbutane, well, they have the same number of carbon atoms, but the hexane is straight chain, not branched, and compared with a branched chain option, it would be expected that the straight chain hexane would have the higher boiling point. If we went cyclohexane, that would have the higher boiling point yet, but the straight chain compared with the branch chain, the straight chain will have the higher boiling point because it can align itself with its neighbors in an optimal way compared with the branch chain. All right, hopefully you got those correct. If not, hopefully at least now you understand why the correct answer is correct. And if you're still lost on these, please do reach out to me for some guidance. Okay, moving on to another property, combustion. We mentioned combustion as one of the key properties of the alkanes, and one of the reasons we care about things like octane is because we use it as a fuel in automobiles. So alkanes contain single carbon-carbon bonds, which are difficult to break, so they don't do a whole lot of chemistry, which is good for you as a beginning organic student, that you've got some classes of compounds that aren't terribly wide in terms of the variety that of chemical reactions that they participate in, but these combustion reactions are the major type of reactions they'll undergo, because even though these are among the least reactive type of organic compounds, they will burn readily in the presence of oxygen. And when they undergo combustion, they produce ideally carbon dioxide, water, and energy as long as there's enough oxygen around. Okay, you have to be careful if there's limited oxygen. You might get things like carbon monoxide, which is very dangerous. So if you are using natural gas or propane or fuel oil to heat your home, you want to be careful that there's enough oxygen getting in there in the furnace or whatever your heating device is, so that you don't make carbon monoxide, which is very dangerous. If you're living in, at least in New York, you have to have a carbon monoxide detector by code in the lowest level of the home with a bedroom. So hopefully you do have that, or you get that now that you know that's the rule, because carbon monoxide is deadly in very small amounts and certainly nothing to mess around with. But as long as we have sufficient oxygen, the alkane will completely oxidize to carbon dioxide, which is not nearly as bad, water, which is just fine, and then all that energy, heat, light, whatever you're using that energy for in your home. Okay, so here we see specific examples. Methane gas is used to cook food and heat homes. It's the least expensive natural gas, as it's commonly known, and again, we have a fair deal of it packed under the ground in the Marcellus Shale formation. If you're in northeastern Pennsylvania, you may have tapped into that resource already. So far in New York, we've been slow to do so, but it is there, and eventually, I'm guessing it will be tapped. And so the CH4 gas combines with 2 moles of oxygen gas to undergo, in the presence of heat, a combustion reaction whereby it releases carbon dioxide gas, 2 moles of water vapor. It's like the gas phase water because of the energy released, because it also releases lots and lots of energy. Propane gas, of course, some homes use that for heating and cooking, but it's more commonly used in portable heaters and gas barbecue grills, and so that requires 5 moles of oxygen for every 1 mole of the propane gas, and it produces 3 moles of carbon dioxide, 4 moles of water, and a lot of energy as well. And finally, our cells themselves get energy from the combustion of glucose. Glucose is not a hydrocarbon, it's a carbohydrate, which we'll learn about later in the semester, but that glucose, which is probably not so much a liquid in our cells as an aqueous solution, plus 5 moles of oxygen yields 6 moles of carbon dioxide plus 6 moles of water plus lots and lots of energy. So there you see some typical combustion reactions. The first two, methane and propane, are actually alkanes, and then finally, because many of you are health science students, I figured I'd toss in the carbohydrate example of glucose, even though it's not an alkane. It is something we will talk about later in the semester. Now, balancing a combustion reaction equation is something that you should have learned back in General Organic Biochemistry 1, but if it's been a while, or if you just never mastered it then, first, of course, you're going to write the equation for whatever you happen to be looking at. In this case, we're looking at liquid pentane reacting with oxygen gas. Remember, oxygen, one of our diatomic gases, is O2, not just plain old O. That triangle above the arrow indicates that there's heat or spark or flame or something to get this thing going. And then finally, our products ideally are carbon dioxide gas and water vapor, and also lots of energy, but that's not technically a chemical quantity. So in the case of the pentane, we've got 5 carbon pentane, so we need to have at least 5 moles of CO2, so we take the subscript of the carbon and make it the coefficient for the carbon dioxide. We balance out the hydrogens now with the waters, so we have 12 hydrogens, therefore we'll end up with 6 water molecules, or 6 moles of water molecules. And then we can balance the oxygens with the O2, so if we have 5 moles of carbon dioxide, that's 10 moles of oxygen atoms, plus 6 moles of water vapor, that's another 6 moles of oxygen atoms, for a total of 16 moles of oxygen atoms on the product side, which would be 8 moles of O2 molecules on the reactant side. So just be careful. Remember, we don't have fractional coefficients in a balanced combustion equation, so if you need to, you'll sometimes have to double everything in order to make it all work out. If you're having trouble with this, even though it is a Chem 141 concept, I'll be happy to help if you reach out for some help to me. Okay, so crude oil. Crude oil is a mix of hydrocarbons, and they're separated by different boiling points, just like we talked about. The longer the carbon chains, the higher the boiling point, and the process by which that is accomplished is known as fractional distillation, where you're removing at different fractions, at different points, different boiling points, the different groups of hydrocarbons by continually heating the mixture to higher temperatures. So you heat it, certain low level small carbon atom groups will come off. So below 30 degrees Celsius, you're distilling what's known as natural gas, which is mostly methane, some ethane, a little bit of propane and butane, those small substances. Then as you continue to heat it, you're now distilling the heavier carbon atom chains, so carbon atoms 5 to 12, and that's gasoline, which is again typically rated by octane, but it does have some other components in it. Finally, as you keep heating, you're going to hit the heavier substances, and that's for kerosene or for jet fuel will be those carbon groups of 12 to 16 carbon atoms. Continued heating gets you even heavier. Things like diesel fuel or heating oil tend to be things like 16 to 18 carbon atom chain lengths, or total carbon lengths if we're dealing with branched or cycloalkanes. And then finally, as you keep heating way up to 350 to 450 degrees Celsius, you're going to get 18 to 25 carbon atom groups, and that would be for applications like lubricating oil. And finally, things that are still there, the non-volatile residue, once you're over 25 carbon atoms, you tend to stick around. That's your asphalt, your tar, your end product there of the natural gas, and obviously that's mainly used at those large carbon atom lengths for things like road work, obviously the asphalt or the tar for those applications. So there we go, crude oil, lots and lots of good stuff there from long dead, mostly plant material. And here we see a picture of that fractional distillation process. So taking that crude oil in, heating it up, and then obviously the Fractions that go the highest are the smallest things that boil at the lowest temperature. So those are your natural gas and then your gasoline. And as you work your way down to the stuff that the sludge, so to speak, that's left behind, that's your asphalt and your tar, which is collected at the end for those applications. So very neat and interesting way of getting all the bang for the buck out of this crude oil. All right, so let's pause here for a learning check. This time you're asked about propane. So propane gas is used to provide heat for cooking. Write a balanced equation for the combustion of propane. Please pause the video here while you do that and then start us back up when you're ready to check your work. Okay, so if you remember, we're looking at the carbon count in our propane to figure out how many moles of CO2 we would expect in our product. So 3 moles of CO2 we'd expect from every mole of C3H8. Then we balance out our hydrogens. We have 8 hydrogens there, so we'd expect 4 moles of water vapor in the products. And finally, we have the 3 moles of carbon dioxide with 2 moles of oxygen in each of those. So there's a total of 6 moles of oxygen atoms there, plus another 4 moles of oxygen atoms in the water vapor to get 10 moles of oxygen atoms on the product side, which means we need 5 moles of O2 molecules on the reactant side. So hopefully you came up with coefficients of 1, 5, 3, 4 if we're looking at left to right reactants then products. If you didn't quite get there, hopefully you've been able to identify your mistake. If you're still struggling, just reach out to me, please, for some guidance. Okay, before we leave this section of Chapter 11, let's have one last learning check. In this case, you're asked to write a balanced equation for the reaction for the complete combustion of heptane, C7H16. So go ahead and pause the video here while you do that and start it back up when you're ready to check your work. Okay, so very similar, just like the previous one. So if you had no trouble with the prior learning check, I'm guessing you didn't have any trouble with this one. But hopefully if you did struggle with the previous learning check, you were able to get this one correct. So we have 7 carbon atoms in each molecule of heptane. So therefore we will expect 7 moles of carbon dioxide gas in our complete combustion of heptane. We have 16 moles of hydrogen, so that's 8 moles of water vapor in the product. And then finally, now if we look, 7 moles of CO2 gives 14 moles of O atoms, plus 8 moles of H2O gives another 8 moles, for a total of 22 moles of O atoms in the product side. And that means we'll need 11 moles of O2 molecules on the reactant side to give an overall balanced chemical equation of C7H16 plus 11 moles of O2 gas yields 7 moles of CO2 gas plus 8 moles of H2O gas. So hopefully this went well, even if the last one was a bit of a struggle. If you're still finding yourself having a lot of difficulty here, please do contact me to get some extra help. Otherwise, if things are going well, and I hope they are, we'll see each other for the last section of Chapter 11.